Today we're talking about taming actual titans. We're going to look at some of the largest structures humans have ever built and the incredible challenge of keeping them standing against the full, raw power of the ocean. I'm talking about these massive offshore platforms and how a brand new approach using AI is completely changing the game.
To just try to picture this for a second, you've got a structure basically the size of a city block or a skyscraper just standing out there in the middle of the ocean. It's getting hammered day and night by waves, currents, you name it. How in the world do you keep something that massive steady? It is a monster of an engineering problem.
And the solution we're about to dive into, it's not just theory. This is all coming straight from new research published in the journal Ocean Engineering. So we're getting the story right from the source, from the very people pioneering this technology.
Okay, first, let's just get a sense of the scale we're dealing with here. Because these aren't just your average little oil rigs. We're talking about true giants of the sea.
You see, these offshore platforms are way more than just for drilling oil. They are absolutely critical pieces of infrastructure. They're vital for energy exploration, they act as huge transport hubs, and some are even used for military operations. They're complex, they're important, and as we're about to see, they can be incredibly vulnerable.
So here's a really simplified look at how they stay stable. You've got the main structure, of course, but inside there's this key piece of tech called an active mass damper, or AMD. The easiest way to think of it is as a giant, computer-controlled counterweight that shifts around to cancel out all that swaying motion from the waves. And that brings us right to the heart of the conflict. It is a constant high-stakes battle. You've got the immense power of nature on one side and this incredibly sophisticated machinery on the other. Now, the problem they face is really coming from two different directions. You've got the obvious one, the external forces, that relentless, chaotic energy of the ocean pushing on the platform. But then there's this other, maybe even scarier threat, an internal one. What happens if the very system that's supposed to protect the platform breaks?
Well, engineers call this an actuator fault. The actuator is basically the muscle of the whole stabilization system. It's the part that physically moves that huge counterweight. If that fails, especially, in the middle of a massive storm, the consequences could be absolutely catastrophic. That's the problem these researchers are laser focused on solving.
All right, so how have we been handling this chaos up until now? Let's take a look at the traditional method. The standard solution is something called active control. And really, it all comes down to a brute force approach. The system feels the push from the waves, and then it tells those powerful actuators to generate a massive force pushing back in the opposite direction to cancel it out. Simple, right? And hey, as the researchers themselves point out, these methods are effective. They definitely do a good job of reducing vibrations. But, and believe me, this is a very big but, they come with a hidden and very high cost.
The best analogy I've heard is that it's like using a sledgehammer to crack a nut. I mean, yeah, it'll get the job done, but it's wildly inefficient. This brute force method just burns through an incredible amount of energy and puts a ton of stress on all the mechanical parts.
And this is where the new research completely flips the script. It's a total paradigm shift. Instead of fighting the waves with brute force, what if a system could actually learn to ride them with intelligence?
The breakthrough idea is to use a type of AI called reinforcement learning. Honestly, the best way to get it is to think about how you'd teach a dog a new trick. You don't write it a manual, right? It tries something, and when it does the right thing, you give it a treat, a reward. Over time, it learns exactly what to do to get the most rewards. The AI learns in the exact same way, just through trial and error. So for the platform, it works like this. The AI tries a tiny little adjustment with that mass damper. Then it observes what effect that had on the platform's sway. Now here's the brilliant part. It gets a reward not just for being stable, but for achieving that stability using the absolute minimum amount of force. It does this over and over, millions of times in a simulation, until it has taught itself the most efficient possible way to handle any wave that comes its way.
So, the million-dollar question. Does this whole smarter, not stronger idea actually work? Well, let's look at the results from the study, because the payoff here it's pretty staggering.
Okay, first things first, safety. This chart is showing how much the platform is swaying back and forth. The red line is the old conventional method, and the blue line is the new AI. As you can pretty clearly see, they're almost identical. The AI keeps the platform just as stable and just as safe as the old brute force way. So big check mark there.
But now, look at this. This is the breakthrough. This chart shows the amount of force, the energy, each system had to use. That crazy red line spiking all over the place, that's the old sledgehammer approach. And the blue line,
way down at the bottom, barely even moving, that's the AI. This is the difference between force and intelligence, right here on a single chart. The actual numbers just make it even more stark. This table shows the average force required by each system. The conventional method needed about 0.93 million newtons of force. The proposed AI method? Just 0.068. The difference is just huge.
When you actually do the math, it turns out the AI-driven system is over 13 times more energy efficient while providing the same level of safety. That isn't just a small improvement. That is a massive, revolutionary leap forward.
And there's another incredible advantage. The traditional control systems, they need a really precise mathematical model of the waves to work right. But the AI, it doesn't. Because it's not memorizing formulas, it's learning principles. It can adapt on the fly. It can handle complex, chaotic, and even completely unknown wave patterns. The exact kind of real-world mess where older systems would just fail.
So what does all this mean for the future? Well, this research really goes way beyond just giant sea platforms.
The big takeaway here is this. We could apply this exact same idea to so much of our other critical infrastructure. Think about bridges swaying in high winds, or power grids trying to handle sudden, unpredictable demand. We can make these things just as safe, but far more efficient. This really marks a fundamental shift away from old-school brute force engineering and toward a future of intelligent, sustainable, and truly adaptive design.
And that really leaves us with a pretty powerful question to think about. If AI can learn to tame the titans of the sea with this much elegance and efficiency, what other massive, complicated problem should we ask it to solve next?